Okay, hi guys. So in this example here, we actually have a crate that's gonna be pushed on a horizontal floor. What happens is the horizontal floor is rough, so there's some friction between the crate and the floor. Okay, let's first draw the free body diagram of the box. Okay, let me set Y this direction as positive and X this direction as positive. Okay, so if we were to draw the free body diagram of the box, what happens is we have the normal force, the weight of the box, okay, and then we have a pushing force. So let me label this as Fp, and we have a friction that opposes the motion, so F friction. Okay, yeah. So let us write down all the relevant equations too for this situation. So in Y, we actually have the normal force plus negative mg equals to 0. Therefore, n is equals to mg. Okay, and then the next part is in x. What happens is we have the pushing force plus negative F friction. Okay, let me put this as ma for now. Although in the first situation, basically there's no acceleration, a is equals to 0. Even in the second situation, a equals 0. But we will actually be using this later. So let me put this as ma. So what happens is we also know the F friction is actually equals to mu n. So I've left mu not labeled, so it could be mu s or mu k, so meaning the static coefficient of friction or the kinetic coefficient of friction. Depending on the situation, whether the box is moving or static, you will use those respective values. Okay, yeah. So therefore it goes, if I were to write this a bit further, so Fp minus mu n, so I can actually replace n with mg equals to ma. Okay, let us look at the first situation. So in the first situation A, it says that there's a pushing force and the box is static, so means that in this case ma is equal to 0. So what happens is, once the box is pushed up to a certain force, then it starts to move. So it means that Fp, let me write this, Fp minus mu mg. So when there's a net force between these two, then the box starts to move. Therefore, if I were to write it, Fp more or very close to mu mg, then the box starts to move. And in this case, because the box is static, I actually will write this as mu s. Okay, so in that case, I can actually find mu s, which is equals to F pushing force divided by mg, and it's given to us that pushing force is 313 over mg, so m which is 45 and g gravity which is 9.81. This gives us a rough value of 0.71 for the coefficient of friction for the static friction. Okay, so now the same goes in the next part where it says that now the person is actually pushing at 208 newtons, but it's moving at a steady velocity. So what happens is there's still no acceleration, but in this situation Fp is actually related to the kinetic friction, which is going to be mu k mg. So mu k in this case will also be Fp, but this pushing force is not the same as the initial 313. It's the 208. So let me calculate that out. So this is 208 divided by 45 g, so equals to 0.472. Okay, let me emphasize a bit more. So as I mentioned, mu s is the coefficient of friction that you use when the objects are stationary, they're not moving yet, while mu k is the coefficient of friction that you use when the object is moving. In this case, it's moving but at a steady velocity. So even in a situation that it has acceleration, you would still use the value of mu k here. Okay, so the next part of the question is, it asks us to find okay, what must you to exert it? Okay, so now in this situation, it's not constant velocity, but we have an acceleration. So we use the complete equation of this. So Fp minus mu mg equals to ma. So what must be the pushing force? I can actually write that, or rewrite the equation. So Fp will be equals to ma plus mu. Okay, so it's moving. I must use mu k mg. So I can actually factor out m, which is 45. So acceleration that is given to us is 1.1 plus mu k, which is 0.71, and we also have mg, g, which is 9.81. Okay, and what happens is it gives us a value of 258 newtons. So we need to push the crate as shown in this diagram at this force of 258 newtons in order to give it an acceleration of 1.1. Okay, let's look at part C now. So what happens in part C, right? Now it's not on Earth. It's somehow the whole setup has been brought over to the moon. Okay, so what happens here is the same formulas are still they still apply. So in the first situation, it's actually push from static. Okay, so it's a case where it's similar to A. So Fp must be more or same as mu s mg. So in this case, again, similar, mu s is actually equals to Fp over mg. Okay, and it's given us the pushing force is oh sorry, it asks us to find that pushing force value. So let me just erase this. So that pushing force, right, will have to be almost or greater or almost equals to that mu s mg, okay, for it to move. And that if we were to calculate out, is going to be 0.71 times 45. Okay, now we have to be aware that g in this situation is not Earth but is on the moon, so this is 1.62. So that gives us a value of the pushing force that's going to be about 51.8 newtons. Okay, yes, and then let's look at the second part. So what would its acceleration be if you maintain the push in part B? So basically it's saying that we use the force of 258 newtons to push it, and what happens in the acceleration value. So we can actually rearrange the formula that we see here in x, that one. So that value of acceleration A would be equals to 1 over m times Fp minus mu k mg. Okay, so in this case g, please be aware it's on the moon, so this is 1.62, and the calculated value, unfortunately due to space, this will be equals to 4.97 meters per second.